Okay, back to 244. Some of you might know that I'm having problem talking, and the problem is still here. Although it's getting much better. Mainly because I have a wisdom teeth growing out, and it has a lot of infections, which caused my mouth is really hard to open. So I try to talk, but I might not be able to talk clearly. I'm taking antibiotics, so the swelling is smaller now, so that's why I can talk a bit. But if it's not clear, just let me know and I'll repeat. Yeah, just a lesson for you. If you have your wisdom teeth, make sure you have them removed, because I've been drinking soup for so many days because I couldn't eat anything. Like my teeth couldn't chew, otherwise it hurts really, really bad, and I uh couldn't open my mouth because of the swelling, and my right ear and my throat are all have infection as well. And also uh oh, I went to the dentist, isn't able to do it himself. Yeah, so let me see. Need to get them surgically removed. Yeah, I'm gonna have mine removed this Saturday, because they were like they need to wait for the infection to be gone, because I couldn't even open my mouth really big. Mm, the drill was so uncomfortable. Yeah, I was really scared of removing teeth, but after suffering from this infection, I don't think I'm scared anymore. Cause yeah, cause I couldn't even sleep at night because it hurts too much. Yeah, yeah. Now I don't think I'm scared anymore. Oh, interesting story. I went to see the dentist, and they wanted to take a picture of my mouth, right? So to put the camera in, but I couldn't open my mouth, and they couldn't put it in. So they want to find the ones for kids and put those in to take pictures, because the swelling was really big, so I couldn't talk. Yeah, I couldn't talk for a long time. Anyway, now it's much better because I'm taking antibiotic, so it's getting much smaller right now. Yeah, I got a full dental checkup. Your molars have to be surgically removed. Oh no. Yeah, I went to the dentist, got the fully checkup, and she was like, "Oh, you have no cavities." And I was like, "Yeah, I've never had a single cavity in my whole life. I know a lot of people do, but I don't." She's like, "Oh, that's great. So you just need to have your wisdom teeth removed." I was like, "Yeah." Anyway, that's my story, and today is our last tutorial, which is sad that I can't really talk clearly, but I'll try to be clear. My plan is to talk power series solutions. So we'll do a short review on power series, and I'll move on to something that's called Euler's method. It's a method for approximation. It's really simple, so we'll talk about it shortly. Even if we run out of time to talk about it, you can just read it yourself. It's really simple. So hopefully I'm not ahead of your lecture, but I know I might be. So first question, did you guys start this power series solution? Did you guys start this? Okay, cool. The S sound is really hard for me to pronounce right now. Anyway, short review. Power series, which looks like this, is set to converge at a point if the limit exists for that x. And we know that it converges for x equals to x 0. It might converge for all x, or it might converge for some values of x, or not for the others. And we say the power series is set to converge absolutely at a point x if, okay, here I'm missing part of the absolute symbol. Okay, if this converge, if it converges absolutely, then it converges, but not the other way around. Okay, and then if the power series converges at x equals to x1, it converges absolutely for, this is minus, not equal, x minus x0 is less than the absolute value of x1 minus x0. And if it diverges at this, then it diverges at this. Okay? And lastly, this is really important because they ask you this a lot, which is the radius of convergence. So if you have a positive number rho called the radius of convergence, such that this power series converges absolutely for x minus x0, the absolute value of this is less than rho, or divergence for this is greater than rho. And you might ask, well, how do I know if a power series converges? Then remember that we have different tests, right? So someone tell me one of the tests you remember to check if a series converges. Anyone remember? Ratio test? Yes. P-test? Yes. So let me just write it here. If you don't remember, you need to check. I mean, you need to review. Okay. Ratio test. This is the one we use the most. Okay. P-test. Yeah. Alternating test. Not alternating. Alternating. Okay. Talking is so hard. Anyway, I guess I have alternating series test. Alternating series. Don't know what's going on here. Another series that you should remember is what's another theory that's really important? Anyone remember? Limit comparison, that's another test. I mean, series, geometric series, harmonic series, and alternating harmonic series. Really important. You should remember those. Okay? You ready here? Yeah, you should have limit comparison. And so on, there are a lot of tests. A few other things you should remember. One is harmonic series. One is geometric. So remember their forms and remember if they converges or diverges. What's the other one? Alternating harmonic series. Okay, make sure you remember those. There are many others, but Ratio test is the one we use the most in this course. Anyway, I can take a break because you guys need to do the first example. Okay, so I want you to determine the radius of convergence of the power series. And if you want, you can write on the board. To help me, you can even present today. This is the last tutorial, and this is what you guys should know already. Oh, and I'll show you Brownie. Oh, today is my cat's birthday, by the way. I don't think anyone cares, but just say in here. Brownie, Brownie, come here. Brownie. I don't think he wants to come. Did I show you my cat? I think I did, right? Oh, Bunny, sit. Good boy. Good boy. Brownie is oh, Brownie is not even 1 year old. It's like yeah, my cat is 4 years old now, and my dog is 9 months old. But he's like 6 times bigger than my cat. We still fight every day. Okay. Can I take it up or no? What did you guys get for the radius or convergence? Okay, I'll take it up anyway. So we can reply. Okay, so this is the solution. Basically, we're just using the ratio test. Okay, so you take the limit as n goes to infinity, and you use n equals to n plus 1, divide by the original, which equals to this, and this will goes to 1, so which equals to this, and we know that it converges absolutely for x plus 1 is less than 2, and diverges when it's greater than 2, which means the radius of convergence is 2. Okay? Any question? Nope. Okay, cool. Then let's do example 2. So I want you to find a series solution in power of x of this equation. Give you some time to work on this. No. I found my cat. But he doesn't get along with my dog. Oh my god. Yeah, they don't get along. They really don't get along. Ronnie, leave him alone. Leave him alone. He doesn't like you. It's okay. I like you. Ronnie, Okay, let me explain what I did. So, first of all, I'm checking if my points, because x is between negative infinity to infinity, I want to check if they're all ordinary points, because if they are singular points, then we have another, that's different, right? So you want to check if your P, Q, R are analytic, and those intervals. So this interval we have here is all real numbers. And since they are constant or linear, we know that they are all analytic. So they're all ordinary points. So we can start this. Okay. So we guessed our solution to be this form, which is a power theory, and we suppose this series converges in some interval. And based on this, you know that your y prime equals to this, y prime prime equals to this, and we sub this and those back into the equation, ODE, you'll get this. So I got one question that why do we need to shift the index? This is because when we get here, you see that well, we have different summation index and they have different powers. What I want to do is I want them to have the same index and the same power. Okay, so I want to fix both of the problem. So what I did is first I want to fix first I want to fix the index of this to 0. So this is what I did. And after I fix this, I got this, but they still have different power. Okay, to make sure they have the same power, I can shift it to sum equals to 1. But what do I do with the 0? Where did I write this? Yeah, I can shift this to sum equals to 1. Okay, because yeah, I shift this to sum equals to 1 and take the n equals to 0 out, so they have the same index and the same power. Once they got the same power, you can combine those two together. And when this equals to 0, you want this term and this whole term equals to 0. So that makes this be 0 and this coefficient to be 0. So if you want this coefficient to be 0, then you need to discuss the next part. We know that A2 equals to 0, and you plug back into this, you will get all of those, which I don't want to use words to explain. You just do the computation yourself. Okay, and once you get all that, you can find your general solution easily. Any other question? Sorry, it's really hard for me to talk. I feel like my throat is on fire now. Here, because you want this whole term to be 0 for all x. You want this to be 0 for all x, so you want this to be 0 and this whole term to be 0 as well. That's why this is 0. Any other question? what if this is because of this recurrence relation? Okay, here, because of this, okay, let me write it in this way. Let's say we put this to the side. So you get m plus 2, m plus 1, am plus 2 equals to am minus 1. Okay? Which means a5 depends on a2, and a8 depends on a5, a11 depends on a8, and so on. Since this is 0, we don't really care what those are. You just know that your a5 is 0. Or you can, okay, let me write it in this way. Hopefully this is more clear. Okay, so if you look at this, since a2, so sorry, I'll just write instead of talk. a2 is when n equals to 3. Okay, does this answer your question? And similarly for a8, a11. Okay, so for every 3 terms, it's gonna be 0 because a2 is 0. Any other question? Okay, seems like we're good. So next part, oh, I should have put this question after this part. So we have something called a function is analytic, which you probably know already. Okay, so some common ones are every polynomial function is analytic everywhere, every rational function is analytic everywhere whenever the denominator is non-zero. And yeah, but generally speaking, it's when the function converges to f of x for all x in some interval containing a. Then we say that it's analytic at x equals to a. And if two functions are both analytic at x equals to a, then their sum product and their quotient are also analytic. And here is a definition. We have ordinary point and singular point. So consider the following homogeneous second-order linear differential equation of this form, where a, b, c are all analytic functions of x. Then we can write this equation in standard form, which means the coefficient of y prime 1 has to be 1. So that gives us this, right? So this is the one I was talking about. Except when I check this, I didn't use a standard form. I just checked all 3 coefficients. Since they are all analytic, I know that well, it's analytic. So if P, Q are both analytic at x equals to A, then the point at x equals to A is called ordinary point. Otherwise, it's called singular point. And about the solution near an ordinary point, suppose A is an ordinary point of the equation. So what you will be given, it's most likely you will be given an ordinary point. That's why you can use this to to find your solution. And most likely they will give you A equals to 0. So x equals to 0. They will ask you to find the solution near x equals to 0. And that's an ordinary point. So you'll get c and x to the power of 1. But if you are doing x is not 0, so A is not 0, then you should do something like this instead. And we have a theory that says the radius of convergence of any such series solution is at least as large as the distance from A to the nearest singular point of the equation. Okay, so this gives you the upper bound or lower bound. Is at least as large. So at least is the upper bound or lower bound of the radius of convergence. Anyone? At least is lower bound. Okay, so this gives you a lower bound. Is it lower bound? At least, so it's bigger than that. Yeah, lower bound of radius of convergence. Okay. So I want you to use this theorem. So copy this, and I want you to use this theorem to find the lower bound of the following differential equation. I don't think we have time to do one more, so we'll stop after example 3. Die. Actually, I'll take it up since we don't have enough time. Okay, that's it. So basically, according to this theory, radius of convergence of any such theory solution is at least as large as the distance from A to the nearest singular point. So we need to find the singular points. And once I write this as standard form, I notice that my singular point is when 1 plus x squared is equals to 0. That's when x equals to plus or minus I, right? So that's my singular point. And the distance from x equals to 0 to x equals to 0 plus or minus, it's the same. So for this one, it's the same. Plus or minus I, it's the same. Okay? And this one should be I. So from here to here is 1. And the distance from x equals to 1 over 2 to x equals to I is this. So if you ask me how do I find the distance, remember the distance function. Okay, that's how I found it. Oh my god. And once you found the distance, you know that the lower bound of radius of convergence. Okay, so we know that this converges at least for x. The absolute value of x is less than 1, and this converges at least for the absolute value of x minus 1 over 2 is less than square root of 5 over 2. Okay, any question? Question? Are we good? Okay, nobody said anything. Thank you, me too. I hope I feel better too. I feel like my throat is on fire now. Anyway, good luck on your final exam. And whatever assignment you have. And yeah, that's it. Not sure if I'll see you guys again, but yeah, good luck on your final exam. And no tutorials anymore next week.